Imagine a world where every single device on your network, think your security cameras, your Wi-Fi access points, no longer needs its own separate power outlet. Seriously, no more crawling under desks, untangling power strips, no more hunting for that one free socket. That's not science fiction, that's the real world magic of power over Ethernet, or PoE. Today, we're taking a deep dive into PoE. We're using a Ruckus Fast Iron Management Configuration Guide as our sort of insider map, our mission. To pull out the really important nuggets of knowledge, we want to help you understand not just what PoE is, but how it's changing, its cool features, and how it helps build these really solid, efficient networks. Think of this as your shortcut, your express lane, to getting up to speed on a technology that's quietly but definitely revolutionizing how we power everything connected. You'll walk away understanding the core ideas, what PoE can really do, and even some of the advanced stuff that makes managing networks, well, simpler and more reliable. Get ready for some aha moments. Those times when it clicks how your devices actually get their power. Now, normally we think Ethernet cables just carry data, ones and zeros, but PoE really flips that script, doesn't it?
Absolutely, completely changes the game. Power over Ethernet, it's a technology defined by the Institute of Electrical and Electronics Engineers. You'll see specs like 802.3AF, 802.3F, and the newer 802.3BT. Essentially, it's about sending electrical power over the same standard network, cabling the LAN cables that carry your data. The core idea, the really revolutionary part, is getting rid of the need for a separate power outlet for network devices. Power and data, one cable. Simple as that.
That sounds incredibly streamlined.
Okay.
But for you, our listener, what does that actually mean day to day? What problems does it solve?
Oh, the benefits are pretty significant. It makes deploying devices much, much simpler, especially in places where getting a power outlet is tricky or expensive or just plain impossible. Think about voice over IP phones on desks, wireless access points mounted on ceilings, IP cameras way up high, even things like point-of-sale terminals, info kiosks, small cell radios for better mobile signals, digital signs. The list goes on. And another huge plus, reliability, because the power comes from a central source, like a switch often backed up by a UPS and uninterruptible power supply. Your critical devices stay powered up, even if the building power flickers.
Right, centralized power. That makes a lot of sense for keeping things running smoothly. So, to really get our heads around this, we should probably define the key players involved in this power exchange, the terminology.
Yes, definitely. Let's nail down the basics. First, you have the IP-powered device, or PD. That's the thing at the end of the cable that needs the power. Your IP camera, your Wi-Fi access point, whatever it is. Then you have the power sourcing device, or PSE. This is where the power comes from. Typically, it's a PoE-capable switch, like the ARC-US devices we're looking at, that actually injects the power onto the network cable alongside the data.
Okay, POD needs power, PSE provides it. Got it. Now, as I was digging through the Ruckus Guide, something really jumped out how quickly this technology has evolved. PoE wasn't always this powerful, right?
You're absolutely right. It's been a journey. The early devices, they didn't need that much power, but technology moves fast, demands went up, so the IE standards had to keep pace, really push things forward to handle these more power-hungry devices. We started with IE 802.3AF. That was the original spec. It offered up to 15.4 watts from the PSE. Good for basic stuff like simple VoIP phones or early access points.
Yeah.
But then devices got more complex. So along came IE 802.3AT, which people usually call PoE+. That bumped things up significantly, delivering up to 25.5 watts of usable power at the device end. This was a big deal. Suddenly, you could reliably power things like pan-tilt-zoom cameras, the ones that move around, or more advanced Wi-Fi access points with multiple radios.
Okay, so more power unlocked new types of devices.
Correct.
And it didn't stop there, did it? We're way beyond that now.
Exactly. The latest standard is IEE 802.3BT. You might hear it called PoE++, or sometimes 4-pair PoE, because it can use all 4 pairs of wires in the Ethernet cable. This standard really opens the floodgates. It supports up to 60 watts for what they call Type 3 devices, and a really impressive 90 watts for Type 4 devices. Now, for you listening, think about what that enables. Powering entire thin client computers directly over Ethernet, driving large LED lighting systems in smart buildings, high-power outdoor wireless gear, things that were just impossible with earlier PoE. It really expands the scope of where PoE can be used. And we should also mention power over HD DASERD, or POH. It's technically covered under an older standard, 802.3 it had, but it can push up to 95 watts. Very useful for things like big TV displays in conference rooms.
90 watts. Wow. Okay, with all that power available, you can't just have it blasting out of every port, right?
Yeah.
How does the system manage this? How does it know what each device needs?
That's a really important question managing the power budget. The IE standards are clever about this. They use a class system. Think of it like a label. Each powered device, PD, falls into a specific class from 0 up to 8. This class tells the power sourcing equipment, PSE, the maximum power that device might ever need. So classes 0 to 3 are mostly in that original 802.3 AF range, up to about 15 watts. Class 4 is for PoE plus the 802.3 AT, needing up to 30 watts from the source. And then classes 5 through 8 came with 802.3 BD, covering those higher power needs, starting around 45 watts for Class 5 and going all the way up to 90 watts for Class 8. This classification lets the switch allocate power intelligently. It doesn't waste power by reserving too much, it just gives what's potentially needed, which optimizes the overall power budget for the whole switch. So a Class 8 device basically says, hey, I might need up to 90 W, and the switch plans accordingly.
That makes sense. It's like a negotiation. Okay, so we know about the power levels in classes, but how does the power actually travel down the wire? Are there different ways it gets from A to B?
Yes. There are essentially two main methods defined in the standards, going back to the earlier ones like .AF and .DAT. The most common is probably N-span power. This is when your network switch itself is the PSE. The power comes directly out of the switch's Ethernet ports. It can use the same wire pairs as the data that's called alternative A, or sometimes it uses the spare pairs in the cable, which is alternative B. The other method is mid-span power. You use this when your main switch doesn't have PoE built in. You put a separate device, often called a PoE injector, in the middle between the non-PoE switch and the powered device, PD. This mid-span injector adds the power, usually using those spare pairs, alternative B. Now, with the newer 802.3b key standard, an important update is that both N-span and mid-span can use all 4 pairs of wires in the cable to deliver those really high power levels we talked about.
Okay, N-span from the switch, mid-span using an injector. Clear. Now, the Ruckus guide mentions some really neat features beyond just basic delivery. Things like ensuring power doesn't drop during reboots. That sounds critical.
Absolutely critical, especially for things like security or communication systems. That feature is called perpetual PoE. It does exactly what it sounds like, provides uninterrupted power to the connected devices, the PEs, even if the main switch, the PSE, is undergoing a reboot or a software reload. Imagine doing routine maintenance on your switch. Normally, everything connected would lose power. With perpetual PoE, your cameras stay on, your phones keep working, your access points don't drop connections. It's a massive boost for network uptime and resilience.
That is huge for operations, and I think I saw something related called fast boot PoE. How does that fit in?
Yeah, they work well together. Fast boot PoE focuses on the startup time after a power cycle, maybe after an outage or just turning the switch on. Instead of waiting for the switch's entire operating system to load up, Fast Boot PoE allows the switch to provide power to the connected devices almost instantly, usually within like 2 seconds. So if the power blips, your critical devices like cameras or phones come back online incredibly quickly. Instead of waiting minutes for the switch to fully boot, it minimizes downtime dramatically.
Super practical, especially where every second counts. Okay, so the switch can keep power on and start it up fast, but how does it know what to power in the first place when you plug something in?
Ah, that's the magic of PoE auto discovery. It's basically a detection process. When you plug a device into a CUI-enabled port, the PSE, the Ricasa switch in this case, sends out a small test signal. It checks if the device on the other end is actually a valid PoE device, a PD, that understands the 802.3 AF at or BT standards. If it detects a valid PD, it then figures out how much power that device needs, usually based on its class, and supplies the appropriate amount. This prevents the switch from sending power down a cable connected to a non-PoE device, like your laptop, which could potentially cause damage. It's a crucial safety and compatibility check.
Right, so it checks first, then powers up. Smart. Now, I also saw this term PoE overdrive specific to Ruckus. That sounds like pushing things beyond the official limits. What's that about?
Yeah, PoE overdrive is a really interesting RRECASA-specific feature. It lets you configure certain ports on specific switch models, like the ICX 7550, 7650, 8200 series, to deliver more power than the standard IE kill classes normally allow. So, for example, a standard PoE Plus port, Class 4, is rated for 30W at the source. With overdrive, you might be able to configure that port to deliver up to, say, 95W. Or, for a high-power Class 8 device that normally maxes out at 90W, overdrive on some platforms might let you push that to 120W. It's managed through something called LLDP M&D messages, basically. The device and the switch have a little chat, and the device says, hey, I know I'm Class 4, but I really need 95W. Can you do it? Okay. It gives you extra flexibility for those oddball, super high-power devices that don't quite fit the standard boxes, provided the switch hardware can handle it.
Okay, overdrive for special cases. Very interesting. So we have all these standards, power levels, features. How do you actually manage all this on a day-to-day basis, keeping the network power running smoothly?
Right, management is key. Rugers offers a few ways to handle power management, or PM. They're a static PM. That's where the switch reserves the maximum power a device could need based on its class as soon as you plug it in. It's simple, but maybe not the most efficient use of your total power budget. Then there's dynamic PM, which is generally smarter. Power is reserved initially, but once the device powers up and the switch sees how much it's actually drawing, any unused reserved power is released back into the main pool. This lets you potentially connect more devices overall because you're not holding back power unnecessarily. There's also a hybrid PM that mixes aspects of both. And of course, you have basic control, like just turning PoE on or off for a specific port using configuration commands like inline power.
Dynamic sounds more efficient. What about prioritizing? Like, if power gets tight, how do you make sure your really important devices don't get cut off first?
Excellent point. You can absolutely set priorities. You configure a PoE power policy. Part of this is setting a maximum power limit per port if you want, using a command like inline power limit. But crucially, you assign a priority level to each port, typically using inline power priority. Priority 1 is the highest, 3 is the lowest, which is usually the default. So you'd give your critical security camera or main access point priority 1, maybe a less critical device gets priority 2, and standard desk phones get priority 3. If the switch ever faces a situation where it can't meet all the power demands, maybe a power supply failed, it will start shedding load by cutting power to the lowest priority ports first, ensuring the highest priority devices stay online.
That priority system sounds essential for resilience. I also saw something about fanless mode support. That seems like a nice touch for quiet places like offices or classrooms. How does PoE tie into that?
It's a great feature for those environments, definitely. Some Archicus switches, like certain ICX 8200 models, are designed to run without their internal cooling fans under specific conditions. The key condition is often tied to the PoE load. If the total amount of PoE power being drawn across all ports is below a certain threshold, maybe 150 watts, for example, and the internal temperature is okay, the switch can keep the fans off, completely silent operation. But it's constantly monitoring. If the PoE load increases past that threshold, or if the switch starts getting too warm, the fans will automatically kick in to maintain safe operating temperatures. It's a smart balance, quiet when possible, cool when necessary.
Very clever. Okay, but even with all this smart tech, things can go wrong. Networks glitch. How do you troubleshoot PoE issues? Say a device just isn't powering up.
Right. Troubleshooting is unavoidable sometimes. Critical thinking, like you said, is key. Rakios provides good diagnostic tools through its command line interface. You can use commands like show inline power to get a snapshot of the whole system, total power capacity, how much is allocated, how much is remaining, and the status of each port, like powering, off, fault. If you need more detail, show inline power detail can give you specifics about the power supplies themselves. There are others too, like show up on client status, which can check the health monitoring status of various processes, including PoE-related ones sometimes. If you see a port that should be powering a device but it's showing off or maybe non-PD detected, these commands help you figure out why. Is the switch out of power budget? Is the cable bad? Is the device itself faulty? There's even a command, inline power couple data link, which can sometimes help in weird negotiation issues, especially with older devices maybe running at slower speeds like 10 MBps. It separates the data link status from the power status for troubleshooting.
It sounds like you have the tools to diagnose effectively. We've really covered a lot of ground today, from the basic idea of sending power over Ethernet cable through the evolution of the standards, giving us more and more power, the different ways it's delivered, and then how to manage and fix it. It's really clear that PoE isn't just a minor convenience anymore. It feels like a fundamental building block for modern networks, making them efficient, flexible, just better.
I agree completely. It simplifies how we build network infrastructure. It definitely cuts down on installation time and cost, and as we discussed, it seriously boosts reliability. It's opening doors for connecting all sorts of devices in places we couldn't easily reach before. It's really part of that bigger trend of optimizing how we power and connect absolutely everything in our digital world.
So, for you listening, as you think about your next network upgrade or deployment, consider this. How much easier, how much cleaner, how much more resilient could your setup be if devices didn't need that extra power cord? From tiny sensors to big displays, imagine them all just plugging into the network for both data and power. Think about the possibility for smarter buildings, streamlined operations, maybe even your own home network. This deep dive really highlights that understanding these technologies, understanding how they work, lets you unlock potential and build better systems. It's knowledge you can definitely apply.